Hello, my name is Kevin Roberts and today I want to talk about matrix diagonalization. We'll go over why diagonalizing a matrix is useful and what it means to diagonalize a matrix, and we'll go over an example of how it's done. So what does it mean to diagonalize a matrix? The main idea is to rewrite the matrix as a combination of other matrices. Typically we can write A as the following, where the first matrix columns are eigenvectors of A. The second matrix is called the eigenvalue matrix, where the eigenvalues of A are along the diagonal of this matrix. And finally, the third matrix is just the inverse of the first. Additionally, from this matrix transformation, we can write A as a summation of rank 1 matrices. Now, why is it useful to diagonalize a matrix? One of the very useful reasons to diagonalize a matrix is to decrease computation time. For example, we can rewrite a matrix A to the 100th power as the eigenvector matrix multiplied by the eigenvalue matrix raised to the 100th power multiplied by the inverse of the eigenvalue matrix. The left-hand side of this equation takes super long for a computer to compute, as opposed to the right-hand side where we're only taking the 100th power of the eigenvalue matrix. Additionally, diagonalizing a matrix is helpful in understanding a system of differential equations, but I won't get into that too much in this video. Before jumping into an example, we have to make sure that matrix diagonalization is even possible. We can check if it's possible by ensuring that A is a square n by n matrix and the eigenvectors of A are all linearly independent. Otherwise, we'd not be able to invert the eigenvalue matrix. Now let's go over an example. Consider the following matrix A. The first step in diagonalization is to find the eigenvalues of A, and to do this, we take the determinant of A minus lambda times the identity matrix and set it equal to 0. Then after doing some simplification, we can see that the values of lambda that will make this equation go to 0 are 5 and 4. Now that we have our eigenvalues, we want to plug them into the diagonal of the identity matrix and subtract A by this matrix. Let's do this for the first eigenvalue. This will give us the following system. After simplifying, we get. Now we want to reduce the matrix on the left-hand side as much as possible. Multiplying -2 times the first row and adding it to the second row to replace the second row gives the following system. Now what we essentially have is one equation with two unknowns, where x2 is a free variable because the second row doesn't have a pivot. We can pick x2 to be anything except for 0 because it's a free variable. But to make things simple, let's pick x2 to be 1. Then we can solve for x1. Now that we've solved for x1 and x2, we can write our first eigenvector to be, and this is the corresponding eigenvector to the eigenvalue 5. The exact same process is done for the eigenvalue 4. We found x1 to be 1/2 and x2 to be 1, so the corresponding eigenvector to the eigenvalue 4 is Now that we have our eigenvalues and eigenvectors, we can write out the eigenvalue matrix and the eigenvector matrix. To find the inverse of the eigenvector matrix, recall the definition of the inverse of a 2x2 matrix. Using this formula, we can easily calculate the inverse of the eigenvector matrix, where A is 1, B is 1/2, C is 1, and D is also 1. Finally, we have found the eigenvector matrix, the eigenvalue matrix, and the inverse of the eigenvector matrix. So we can rewrite A as a combination of these matrices. Going back to our particular example, we have the following matrices. So we can rewrite A as a combination of rank 1 matrices, using the eigenvalues and the eigenvectors multiplied by the rows of the inverse eigenvalue matrix. It's important to note that these rank 1 matrices also have one pivot. This means that their column vectors are not linearly independent. That concludes my video of matrix diagonalization. Thank you for watching.